and welcome to this lecture. This lecture we are going to continue our study of the covariance matrix. In particular, we are going to look at a very interesting property which is called the positive semi-definite matrix property. Okay, so let me define what a positive semi-definite matrix is. It looks like a complicated word, but you will see the definition is quite simple. If you have a real symmetric m by m matrix A, this matrix A, it has to be real and symmetric. Okay, so that's how I am starting. If it is said to be positive semi-definite, if the quadratic form, right, x transpose Ax is greater than or equal to 0 for all x in Rm. Okay, so now you see where the positivity comes from. It says positive because it has to be greater than 0. The semi-definite because it's greater than or equal to 0. So if you say strictly greater than 0, you can say positive, but usually positive definite. This word semi comes because you're making it greater than or equal to. Okay. So we'll use positive semi-definite throughout. It's a much easier thing to handle. So what should happen here? If I have a real symmetric matrix A, I know the quadratic form is there, x transpose Ax. If the quadratic form for all x is non-negative, then we say A is positive semi-definite. Now here is a couple of ways of interpreting this. First of all, what it means is that the quadratic form defined by A has to be non-negative throughout for all x. And one more definition here, this is a matrix definition. You also have a corresponding operator definition. The operator represented by a positive semi-definite matrix, we will say is simply positive. Okay, the positive operator is the operator represented by this matrix. Okay, so this is just some definitions. Now what is very interesting is the covariance matrix Cu that we defined earlier, right? Do you remember the covariance matrix? That covariance matrix is positive semi-definite. Okay, so that's a powerful property. It's not just merely symmetric, it is positive semi-definite. The quadratic form that it defines never takes negative values. Okay, so here is the proof. The proof is actually very, very easy. So if you look at x transpose Cux, you write out the definition for Cu, right? So Cu, I'm going to write a simpler definition here. Normally it has to have the u1 minus u bar and all that, so I'm just swallowing that u bar into the u1 definition. Just imagine u1 is centralized already. Okay, so it's an easier way to write. It doesn't change anything, it's just another vector, right? So what I have for the Cu is 1 by n u1 transpose plus so on till u1 transpose, right? The minus u bar I've just swallowed it, so that make it redefining u1 like that. Okay, so you get this as the expression. Now once you get this expression, you can multiply the x transpose inside and the x inside. So you will get like this. So every term has an x transpose here and x here. And here is the crucial observation. Notice this, x transpose u1 and u1 transpose x. What are these? X transpose u1 and u1 transpose x. These two are actually scalars and they are both equal. They are transposes of each other, right? Do you see that? They are both scalars, right? So first of all, this is just one dimensions because I am multiplying u1 transpose by x. So it is just a scalar, it's a real number. And if I take its transpose, I get this. So these two are actually equal and they are both real. Okay, so very curious little construction that you have here. So once they are equal, I can simply substitute both by itself. So I get x transpose u1 squared plus squared so on, and this will be greater than or equal to 0. Okay, so I have a sum of squares, n of them, I'm dividing by n, there's nothing negative here, it's going to be greater than or equal to 0. So here is a crucial, very interesting property for the covariance matrix. Not only is it symmetric, but it is positive semi-definite. Okay, so that's a very powerful and very, very interesting property for the covariance matrix. Okay, so here is something about the eigenvalues of a positive semi-definite matrix. See, if you have a real symmetric matrix, A, let's say is m cross m, the real eigenvalues are lambda 1 to lambda m. We know eigenvalues are real. It will have orthonormal eigenvectors v1 to vm. Okay, and I know I can write A as lambda 1 v1 transpose plus so on till I'm missing a lambda m here. Okay, so A itself has the spectral decomposition which we have seen before, the orthonormal diagonal equivalence, similarity, right? So you rewrite that in this fashion. So lambda 1 v1 transpose plus so on till lambda m vm transpose. Okay, so now when is this going to be positive semi-definite? Let's do the x transpose Ax. If you do x transpose Ax, notice what you get here. It's x transpose times this matrix A times x. Now I can push the x transpose as an x inside. So I'll get, for each term I get a x transpose v1 transpose x. Now again you use this same thing. Notice that these two are actually equal, right? They are just transposes of each other and they are just scalars. So these two are equal. So by the same logic you can say it's lambda 1 times x transpose v1 squared plus so on till lambda m x transpose vm squared. So this is just an inner product of x with v1, and v1 to vm are all orthonormal, right? So how is this going to be positive or negative? These guys are all squares, they are all positive. So everything depends on the signs of lambda I, right? If any lambda I is negative, you are done. You can make the whole quadratic form negative, right? Because I can pick x to be along just that negative guy, I will get a negative value. But if all the lambda i's are positive, then this entire quadratic form is positive. So, that is a clear argument you can make from this form, the diagonalizable form of the symmetric matrix. So, you see that the quadratic form is greater than or equal to 0 if and only if all the eigenvalues are non-negative. So, that is a crucial property. So, eigenvalues of a positive semi-definite matrix are non-negative, and a symmetric matrix is positive semi-definite if its eigenvalues are non-negative. So, if and only if, okay, a very easy condition to check if a symmetric matrix is positive semi-definite. Compute the eigenvalues, they have to be non-negative, then it becomes positive semi-definite. Okay. So, finally, let me just conclude with another type of getting positive semi-definite. So far we looked at the covariance matrix and it was positive semi-definite. Here is another way in which you can generate a positive semi-definite matrix, which has a lot of applications all over in linear algebra. Okay. So, here is the starting point. Let us look at a transformation T from Rn to Rm, a more general transformation. Okay, it goes from Rn to Rm, it is not even an operator. So, A is the m by n matrix which represents this transformation, let us say in the canonical basis on both sides. Okay, so, that is the matrix A. So, you can define the new operator T star T. What is this operator T star T? It is an operator from Rn to Rn, right? Because T goes from Rn to Rm and then T star brings you back. So, T star T is an operator from Rn to Rn. What is the matrix representation of that? We know T star has a matrix representation A transpose, right? So, we are going to assume orthonormal basis here. So, it is A transpose, and then T has a matrix representation A. So, T star T has a matrix representation A transpose A. Okay. So, likewise, I can also define another operator T star. Now, T star will go from Rm to Rm. Okay, think about why that is true. T star takes you from Rm to Rn, and then T brings you back from Rn to Rm. Okay, so T star is an operator from Rm to Rm. Okay, M to M. Now, this guy is represented by A transpose. Okay, so keep this in mind. So, if you have A being an m by n matrix, you can define two square matrices related to A. One is A transpose A, which is an n by n square matrix. Another is A transpose, which is an m by m square matrix. Okay, so that is the upshot of this discussion. So, given any transformation in any m cross n matrix, rectangular matrix, I can define two square matrices sort of connected with each other, which is the matrix transpose product, A transpose and A transpose A. Okay, very important. Now, here is the very interesting property. Both these matrices are positive semi-definite. A transpose and A transpose A are positive semi-definite. Okay, so here is another very powerful way to come up with positive operators, and the proof is very simple. You start with an x in Rm, you look at the quadratic form x transpose A transpose x. This is nothing but identify this part as the transform of this guy, as the transpose of this guy, right? Okay, so this is just the vector multiplied by transpose on the left, and that is the inner product, right? So, and the inner product of this is nothing but the norm square. Norm square is greater than or equal to 0. Okay, so very easy to show A transpose is positive semi-definite. Same thing for A transpose A. Okay, so the proof is okay, but basically if you do this, you go from a rectangular matrix to a square matrix in this form, you get a positive semi-definite matrix. Okay, so in fact, the eigenvalues of T star and T star T play a very important role. The eigenvalues of A transpose and A transpose A, the eigenvectors of A transpose and A transpose A play a very important role in what is called the singular value decomposition of T, and any operator from Rn to Rm has something called a singular value decomposition. Just like the symmetric matrices have this decomposition property, singular value decomposition is a powerful property for any operator. We are not going to do this as part of this course, but if you are interested, you can read further. You will see there is a very nice decomposition that's of interest in all applications. Okay, thank you very much.